All right. So physics is neat. I think that's an understatement, but physics is neat primarily because we can take all of the complications of the real world, right? And we can ignore so many things and still get good usable answers, okay? For example, um, Newton gave us the equations of motion that tell us how the planets move around the sun, how the moon moves around the earth, right? If I wanted to, I could take information about, let's say, the moon. Let's say a planet around the sun, any planet around the sun. And if I wanted to know the motion of that planet around the sun, well, what's a planet made of? Particles, many of them, right? Okay, atoms. I could list, this is important, I could list the location and the velocity, so position and velocity, of every single particle in a planet, and using all of that information, way too much information, the position and velocity of every single particle in a planet, I can tell you what the planet's going to do, how it's going to move around the sun. But that's extremely calculation dense. There's something like 10 to the, oh, I'm going to get it wrong, but it doesn't really matter, 10 to the 50 or so particles in a planet. Okay, that's a lot. It's 10 followed by 50 zeros. Okay, I don't need to do that though, right? What do I need to do to tell you how a planet's going to move around the solar system? All I need to tell you is, what is the center of mass of that planet doing? What is the position and the velocity of that center of mass, right? That's the simplicity. That's why physics is great, because I can simplify. I don't have to tell you what all of the particles in the planet are doing. All I have to tell you is what the center of mass of that planet is doing, and that's sufficient to tell you everything else you need to know about what the planet's going to do. Okay, so physics has this incredible property that we can simplify things down to the most basic levels and still recover answers, good information about the world around us. So that's why physics is successful, because we can, using Occam's razor, right, we can ignore a ton of things, namely in planetary motion, the position and velocity of every particle, and we can still recover what the planet is going to do, or what anything is going to do, really, because physics tells us the equations of motion for anything, not just planets. So huge success that we can reduce all concepts to their simplest forms, and in physics we can reduce all measurements into 3 fundamental units of measure, and everything else can be derived, figured out from that. Okay, that's the first lesson in entry to physics, is that we only need 3 units of measure to talk about anything in physics. Okay, we need a unit of time to tell you how much time has elapsed in any given situation. We need to be able to measure space, the 3 macroscopic dimensions of space: up, down, left, right, forward, backward. We need to be able to measure those. To do that, we have to be able to measure length. So length is a fundamental unit. Even though, as Einstein told us, that length is space is flexible. Okay, but what you're learning here right now is called classical physics. Classical physics deals with fixed space, fixed time, nothing changes like in relativity. That stuff I showed you about relativity, that is, the cherry on top of everything. We got to get through all the, the rest of the cupcake first, okay? So we learn classical physics, and really everything you need to know about radiography really deals with classical physics. Relativity is important to understand conceptually, but doesn't play a big role in our down-to-earth physics understandings. Anyways, all right, so we need to be able to measure time, how much time has elapsed. We need to be able to measure the dimensions of space, what's the distance to things, and then we need to be able to measure mass. Mass, as you're going to learn, mass and weight are different. Okay, there's a relationship between mass and weight, but they mean different things. We'll talk more about that in a moment. So physics deals with 3 fundamental units. Everything else is derivable. Okay, for example, speed, velocity, right? What is velocity, right? Tell me how fast you drove coming here. Taylor, how fast did you drive coming here?
Jessica drove 95.
Jessica drove 95 miles an hour. Okay, so you told me she drove 95, right? That's fine. You made it though. Please, I'd rather you be late than drive fast. It doesn't matter. The point. The point. I'd rather you be safe, but anyway, the point is, okay, when you tell me Jessica drove 95, right? What are you telling me? You're telling me she drove a certain distance over a certain amount of time, right? That's not a fundamental unit. Miles per hour is not a fundamental unit. 95 miles over a time of an hour. Okay, in 1 hour's time, she drives 95 miles. Time and length, miles and time, are parts of that the velocity, but they are independently the fundamental units. And we built a derivable unit of velocity, speed, distance over time. Okay, so these are our three fundamental units that we use. Then there are the forces that act on other things. Okay, so and we'll talk about these forces more in depth in just a moment, but just to get them out there, everything in the universe is governed by one of these four forces. Okay, there's gravity. Gravity is actually the weakest possible force. Okay. Of all these forces, gravity is weak. Gravity seems strong because we're on a big giant rock, right? Every piece of matter has a gravitational attraction to every other piece of matter, okay? We all have a gravitational attraction to each other. We don't notice it because we're very small, okay? Our gravitational field is extremely small, right? We notice the Earth's gravitational field because the Earth is very, very big, right? We notice the gravitational field of the moon. What does the gravitational field of the moon do for us? Giving us tides, more importantly, right? So as the moon moves around the Earth, it pulls up on the ocean, and as it rotates around the Earth, it drags the ocean with it. Okay, the actual and it does it to us too. There is a measurable distance that the moon pulls on the Earth's oceans, and all of the Earth, but the oceans are liquid, so they move. It pulls on everything, the solid stuff included. So gravity is purely an attractive force. That's all. Gravity can never be repulsive. Okay, there's no in the real world such a thing as negative gravity. Gravity is always positive, right? Take a thing and a thing, they will always have a gravitational attraction to each other. Okay. Then there's the weak nuclear force. The weak nuclear force deals with radioactivity. It's what's responsible for when neutrons radioactively decay. You guys recall in the video Tyson mentioned neutrons. He also mentioned things called neutrinos, the ones where there's 65 million of them passing through every square centimeter of your hand right now, right? They exist because of the weak nuclear force allowing that. Okay, that's a complicated one. We don't spend really any time on it. We just say the weak nuclear force is involved in radioactive decay. Okay. Nextly, electromagnetism. This is the phenomenon of interactions between electrons with their electric field and the magnetic field they create, and all propagating electromagnetic waves, meaning light, radio waves, X-rays, those things. That's a force. And lastly, the strong force. The strong force is what bonds the nucleus of atoms together. Okay, so we've got our four forces and three fundamental units. Okay, so let's talk about where we get these from. Time, nowadays, is based on something called cesium. Okay, so there's an element called cesium, and we know from experiment that, so everything, all atoms are always in some state of motion, okay? Atoms vibrate. They always have kinetic energy, motion, vibration, okay? We know that cesium from experiment vibrates at an exact frequency. So we can say that, and we do this by measuring the light that cesium gives off, okay? So we know how many times in a second cesium vibrates. So we say that And I don't bother, I have it in a PowerPoint, I don't bother telling you the exact number of times in a second cesium vibrates, because it's not that important, right? But we know, or we say that in an atom of cesium, over 1 second time, it vibrates a certain number of times, and it never changes, okay? So we say that the second is how many, is this many vibrations of cesium, right? Every time this atom of cesium vibrates this many times, we say that's 1 second, okay? You guys know your phones keep pretty accurate time, right? To do that, they have to receive a signal from the atomic clocks in Colorado. Okay, it's where the atomic clocks are kept. And you know, several times a day, your phones are receiving, requesting and receiving a signal from those atomic clocks that use cesium atoms to keep accurate time. It's how we keep accurate time here on Earth. It's how our phones keep accurate time. Any device connected to the internet that keeps time is receiving a signal from those atomic clocks telling it what time it is.
The number is 9.2 billion.
Is it? Okay. 9.2 billion? You sure? I have it.